So in this lesson, we're going to go over how square roots can be used to solve equations. And we're going to look at first how to evaluate a square root of a perfect square, and then look at just a tad bit about non-perfect squares. So first, some vocabulary. So one of the things I'm going to go over is the correct terminology, and that's one of the things is that this symbol, even though most people pronounce it as the square root symbol, it actually is called a radicand, and that's because it does more than just take square roots. If later on in your math careers, you're going to be learning about that it could be used for things like cube roots, and so you might see it written with a little number here in the corner, and if it has a little 3, for example, it's a cube root. It might have a 4 for a fourth root, but without a number there at all, it's understood to be a square root. The number underneath it is called a radical, and the answer is called a root. So when we're evaluating, we look for a number times itself, which equals the radical. So to get the square root of 36, we want to know a number times itself, which equals exactly 36. And in this case, since 6 times 6 is 36, the square root of 36 is 6, or the root of 36, sometimes people would say, is 6, excuse me. So the square root of 49, we are looking for a number times itself, which would give us 49, and that would be 7. So 7 times 7 is 49. So the square root of 49 is 7. So 225, if you don't know off the top of your head, that's okay. We can factor it. So I know that 9 times 25 is 225. And 9 is a perfect square, and 25 is a perfect square. I know that the square root of 9 is 3, and the square root of 25 is 5, so the square root of 225 would be the square root of 9 times the square root of 25, which is 15. Now, this number here has no perfect square, and that's because no matter how we try and break it down with a factor tree, it's 1 times 45, I could do 3 times 15, I could do 9 times 5. There's no way to get it down to a number times itself. So, because I cannot get it down to a number times itself, we know it's not a perfect square. If I went ahead and did it on my calculator is going to give me something that's in decimal form, but it is not going to be the exact square root. It's what we call an irrational number. But I can get close to it by looking for a factor that is a perfect square in it, and we saw that when we made it 9 times 5. So I can break it down into two separate parts. It's perfect square part, 3, times its non-perfect square part, square root of 5. So this would be another way of writing a non-perfect square as its perfect square root times its non-perfect square root. Okay, so now we're going to go ahead and we're going to move into why square roots are important in terms of algebra solving. So we've learned that every operation in math has an inverse that we have learned in elementary school. Adding, the inverse is subtracting, and subtracting's inverse is adding. Multiplying's inverse is dividing, and dividing's inverse is multiplying. Well, when you square a number, it too has an inverse, and that inverse is square root. And square root has an inverse, which is to square. So here in this equation, this says this number got squared, and when we squared it, we got 25, and we want to know what that number is. So I'm going to undo squaring the number. Well, the inverse of squaring is the square root. So I'm going to take the square root of both sides of an equation because properties of equality says whatever you do to one side, you do to the other. Now before I go on, I'm just going to remember one thing that we learned about exponents. And that was that whenever we square a number, like 6 or 7, let's go ahead and do 7. 7 squared, I get 49. But if I square a negative number, like -7, I also get 49. So here, do I know if this number that I squared was positive or negative to begin with? I don't. So in algebra, I have to include both possibilities. So we use this symbol, and it's pronounced plus or minus. And what it means is include the positive and the negative possibilities. So what I do is right here on my right side, when I'm evaluating the root of 25, I say include the positive and the negative of this root. It goes on the outside of the radical. So the square root of x squared is just x. The square root cancels the squaring. So that leaves me x by itself plus or minus the square root of 25, which is 5. So that means x is 5 or x is -5. So let's verify that solution. So if both of these are valid solutions, when I go ahead and plug either of them into the equation, they both should come out to give me positive 25. So positive 5 squared, 5 times 5 is 25. So it works. -5 squared, remember a negative times a negative makes a positive. So it also gives me 25. So that means both of them work. Okay, so let's go ahead and go on to this one here. A squared plus 15 equals 51. So my job is to get the variable by itself. Well, order of operations, we square and then we add 15. So remember, we reverse the order of operations, which means I got to get rid of adding first. So the inverse of adding 15 is subtracting 15. So I'm going to subtract 15 from both sides. So that's going to give me a number squared plus 15, take away 15 is 0. Then 51 minus 15 is 36. And now I'm going to do the inverse of squaring. And so as soon as I take the square root of both sides on that, where that 36 is, I'm going to put that plus or minus. So don't forget it. So the inverse of squaring is the square root and plus or minus 36. So I got a, and the square root of 36 is 6. So now we verify. A number squared plus 15 is it equal to 51. A number squared plus 15 is it equal to 51. So if I plug in positive 6, -6. 6 squared is 36. 36 plus 15 is 51. Sorry for the messy. Works. Negative times a negative is a positive. 6 times 6 is 36. Plus 51, or 15, I keep saying that, is 51. And it works. Okay, that's it.